Hello, everyone. It's really packed in here. Thank you all for coming. As Vanessa already said, my name is Madlaina. I am from Switzerland, and I'm a game designer and currently a full-stack developer at Archelogic. We are working on a toolkit in JavaScript to provide 3D models for interior spaces and also APIs for spatial analytics. So what we do is we want to make 3D models accessible for every web developer that would like to integrate this in his daily work. As I studied game design, I'm really excited about games, as you might see there. I love to play games, I love to collect retro games, and I also love to make games, which usually includes working in 3D. I also really love traveling, as I see it as a resource for a lot of inspiration, especially for storytelling and finding new ways of designing. And I also love creative things and music and a lot of other things, especially Iceland. I've been here 2 times already for a long period of time. I have not seen anything. So, you definitely have to come back. Why should you, as a web developer or JavaScript developer, be interested in doing 3D on the web? As we might already know, most of you guys, folks, as might everybody know that WebVR is coming. And 3D on the web is very accessible at the moment. And we're also challenging browsers, like Jean-Yves was explaining before, to actually support 3D on the web. There's lots of things you can do to enhance your product. For example, this is a screenshot from what we are doing. We are having semantic 3D models, which we can then analyze with machine learning for spatial data. And we can actually also use machine learning to propose you how you should furnish your apartment, which is pretty cool. So you can see your new house already before it's actually being built. Or you can make really cool small games on your browser, on your website, integrated it with all the native web environment things that you have, and you can make them work with each other, which is really cool. You can also use it to enhance your infographics or to make your data more readable with enhancing it with the 3rd dimension. So you can also use animation, time, and the 3rd dimension to show something you would like to do with your data. I think this is pretty interesting, and you should definitely think about how to use it. Most developers that would like to start with especially WebVR have been coming to me and ask me, how do I get started with 3D? Why is it that it's so hard to get started for these people? And this is what I would like to talk to you about today. I would really love that you come out of this talk and you have this little toolbox with things you have heard before and you feel more motivated to start trying it. Because at first, you will be overwhelmed by all the new terminologies you're going to encounter. Not only have you new things to learn, but you're also going to be a movie screen designer. You're going to be a narrator. You're going to have to learn how to do UX in 3D. You're going to have to learn about 3D modeling, how to light a scene properly, etc., etc. That's a lot of things to learn. I would like to talk to you first about the physics of light. So here you see a very simple scene. We have this little apartment. Yeah, it works, okay. And we see a computer standing on a desk, we have a chair, we have a window, and outside we have the sun, which is primarily the source of light, which makes us see everything. But how does that actually work? So every light source, for now we're talking about the sun, is emitting rays of electromagnetic waves. As soon as these rays are hitting an object, they are going to interact with that object. So either the object is absorbing all the light, in that case a lot of energy is being produced, or parts of the ray of the sun are going to be bouncing off and reflecting on different surfaces until that light energy is used up. So I already said that. The electromagnetic waves consistent of different frequencies, so that means different frequencies are different colors. If one frequency is absorbed, the other two frequencies are going to hit our eye, the retina of our eye, therefore creating this color in our eyes, and we can see it. Different materials react very differently, which I'm going to talk about the differences afterwards. But there is three major things, as I said already. It's absorption, reflection, and transmission of light. We can see this here a little bit more graphically. Imagine you have a perfect mirror, which is it's not possible, even if we polish your surface very well, you're never going to have it, but theoretically, a perfect mirror will reflect all the light rays uniformly. This we call specular reflection. Then we have diffuse material like cloth and like wood and other things that are not so much reflective. So it's gonna take the rays and bounce them back in a very chaotic way. And you have propagated light. So if you have glass or water, the light is not only gonna reflect, it's also gonna transmit through the solid, creating these really cool effects. So this is of course not everything that defines a material, but as we can see in this illustration, these three components make a lot of our real life materials. And it's never just one component that is there in one material. For example, if you imagine you have a wooden floor that is not polished, the rays of light are going to bounce back chaotically. But if you then put a polish or a finish on, it's going to be very shiny from specific angles. And that's what I really want you to think about when you get started with 3D, because that's what a lot of people get wrong. Or just don't think about, because why would you? So how do we now translate this into computer graphics? I would like to just go back to a few centuries back where the first cameras were appearing. And these are called pinhole cameras. So you have a light-sensitive film on the back of a box with a little hole inside. And only one ray of light per angle is allowed to pass through that hole, creating then the color on that spot of the film. And we are also using this technique in the render engine technique called Raytracing, and that's what I'm going to talk about. However, if you imagine again the sun, it's not only shooting one ray at a time. It's like a really, really big energy source, and it's shooting down all these billions and billions of rays at the same time. And most of these rays are never going to hit our eye. They're never going to hit our camera or whatever specific spot that we want to look at. So what computer graphics are doing is they use a technique called backwards ray tracing. So we are tracing the rays, but instead of going from the light source, we're going from our camera through the pixel that we want to trace, and we shoot a ray into the scene, and we look at the first object that we're going to hit, at the closest one. From there, we want to see if this one object is in shadow, or if it is in light. Okay, so if the object is actually lit, we're going to use the color of the material that is defined at that space, basically multiplying it, simplified said, multiplying it with the color of the light, the intensity of the light. If the object is in shadow, we're just going to use yeah, we're just going to use black for now as for shadow. This is very simplified. But now, I also talked about these other things that are called like transmission and reflection. So how are we handling this in ray tracing? Imagine we want to see where, if we have a transparent material like glass, we would like to see what can we see through that glass and what is reflected on the surface of that glass. So on the impact point, we have to calculate the different rays that we're going to trace. One of those rays is going to be the reflection ray, and one of them is going to be the refraction ray. It's a bit, yeah, not very nice that the names are so close. And from there, from these rays, we're going to do another check if they are hitting a next object. So if the reflection ray is hitting this red sphere, it's going to be red at that point. But the refraction ray is hitting this green sphere. And so we have to calculate together if we want to have the pixel there red or green. From the impact point of the secondary rays, we're going to trace towards the sun and see if these points are in light or not. I want you to have a moment to look at this code. Did everybody get it? Can you come here and explain it to me? Because this is how I feel about my own code after 2 weeks of not looking at it. So yeah, what you're looking at is a basic implementation of a ray tracing engine that can do reflection and refraction with geometry primitives of spheres. And I'm not sure if planes as well. I think only spheres. And this is a common challenge among people who do computer graphics, is how to make the most compact ray tracing engine that can be fit on a business card. So this actually compiles, and I think that's pretty cool. But let's take it apart a little bit. So what we want to do is we want to define our geometry primitives. And for now, we are just going to talk about a sphere, because a sphere is one of the most easy shapes to calculate intersection. And for that, we need a center and a radius, and we want to have the material, because as I explained before, that's the most interesting part. And we're going to make an algorithm that will calculate our intersection from that. If we are successful, we're going to return both points that are intersecting with the sphere, because usually you will have two of them. So the distance to the closest one and the distance to the further away one. Then we're going to start our main function, and we're going to define the geometries. And again, for simplification, our light source are also going to be spheres, just with a different material that actually emits light. For that, we can test afterwards. We're going to have a buffer for our canvas, and we're going to go and traverse through each pixel. And we're going to trace for each pixel one ray. That's what we did before, right? Then in the trace function, we want to see again, we shoot this is the primary ray that we talked about before. And we want to see which is the closest object. So we're going to test the ray against every object in the scene. And as a result, we get the nearest one back. If we don't have one hit at all, we can just return a background color because there is nothing there. And there will never be something there. That's the really cool thing about ray tracing. You actually test against the whole scene. If there is an object there and it's a transparent or a reflective material, we're going to have to shoot the secondary rays for each of those. And we do this recursively until we are satisfied. And usually you don't want to do this endlessly because it's going to take forever. So we're going to decide how often you want to do this recursion. And at the end of that, you will test against the lights and see if these points are in shadow or not. Then you're going to use a Fresnel algorithm to see how you should calculate the lights together, or the results of the colors you're getting. I'm not going to explain that right now, but it's very interesting to look at. And if it doesn't fall into this, that means we are hitting a light source or a diffuse material that is not going to reflect any different points, so we can break the recursion there. I did not make another slide for this because I think it's clear. And this is the result that we are getting from this. And I think it's very interesting to see that from this rather simple algorithm, we already get really cool effects. Like we can really see the spheres that are close to each other, reflecting each other. We can see shadows, and we can also see what's behind the camera, which is pretty cool. And this is something that you do not generally see in games, for example, or in different render engines. And why is that? We're going to get to that later on. So this was really easy, I think. But now we want to really go realistic, because we said before, there is not one ray per pixel. Usually the sun shoots so many rays that make up 1 pixel of your image. There is so many things that come together. We want to have soft shadows. We want to use multiple light sources. How are we going to compute these together? How are we going to decide on what is more weighted, which pixel should be what? And we really want to have this physical correctness, which means that we have to basically bounce the ray forever until it hits the light source by itself. Right now, we're just making a shortcut because we just test if it will be hitting the light or not, if there is something in between or not. This is going to use a lot of computational power. Ray tracing is a really old technique. It's from 1984. Was the first SIGGRAPH conference that was taking this as a topic. And since then, we're still not there where we have real-time ray-traced engines that are working. It has a lot to do with this, that you cannot make shortcuts to make it look good. You have to have a certain amount of samples, unless you're going to have otherwise you're going to have a really noisy scenery. Yay! So we have a lot of new light sources in the room that are also casting rays. I would like to just very briefly introduce to you rasterization technique. This is the most common real-time render engine technique that is being used. And it's just as ray tracing, it's just as fundamental, this technique. It has been around almost the same time, because when ray tracing was introduced, the computational power was not good enough or not strong enough. It would have taken them forever to render 1 frame of an animated movie, for example. So what's interesting about rasterization is that it's also trying to solve the visibility problem. It's also trying to find out which object is laying in shadow, or what's the color of it. But it's doing it in a very opposite way of ray tracing. While ray tracing is going from the eye or from the camera into the scene, rasterization is going from the objects or from the scenery onto the screen due to perspective projection. So we take all the numbers and all our points and all our vertices, everything, and we project it onto the screen. For this, it's currently using triangles, which is also a rendering primitive. The cool thing about triangles is you cannot subdivide it anymore. You cannot make more areas out of it. And the areas is always planar, so we never have like a perspective warp or something, which makes it really cool to then project and test. What we then do with the triangles that are mapped onto screen space is something that also Jean-Yves has been talking about before. We are rasterizing each pixel for each triangle that is visible, and we map their z-value, so how far it is away from the camera, so that afterwards, when we color it in, we know what's on top of each other. And if we have transparency, then we have to consider the z-buffer, because that's how we're going to put it together. Which also tells us that the z-buffer is basically, so a transparent object is basically just a look-through with a different alpha value, which does not have this refraction rays that are kind of warped around in the scene. So here in this image you can see two basic implementations. One basic implementation of rasterization and a basic implementation of ray tracing. And you can already see the difference, I think. While rasterization has come a really long way, if you have played any 3D games recently, or if you are working with WebVR, you're going to know that it's not going to look like the image up there. So there is a lot of simulations of real physics happening in rasterization. But generally, this implementation is also really a lot of work to do to simulate these physics. But they are doing a pretty good job. The only problem is still transparency, I think. So just a quick overview of the two. Ray tracing is mostly physically correct if you put enough effort in it. It has very high details, very nice side effects that you don't have to think about. You get the soft shadows, you get the reflections, you get the caustics. But it's very computationally heavy. So we are going to use a lot of computation time to render frames. And if we ever want to do this real time, we're going to either have to break it down or we have to make cuts. And rasterization is super fast. It's really only one transformation, basically, from your world coordinates to your screen space coordinates. There's a lot of tooling and hardware support, so your GPU in your computer is designed to do rasterization. It's not designed to do ray tracing. And most of the, like Pixar and most of the rendering people I know, they're still rendering ray tracing with CPUs, because it doesn't matter to them if they are 3 times faster or not. What matters is that they have to change all their tools, and they have to change their engines to be supportive of GPUs for just a little benefit. So you have the physics that are not really correct. You have like an approximation of what you can do. And you have quality loss due to that. So this is kind of the point where I hope you are all, oh God, how should I even get started? It seems very complicated. So I would like to introduce you A-Frame Toolkit. And A-Frame is a web toolkit where you can really easily get started with making your own 3D scenes. And if you're a fan of HTML, you're going to be really happy, because this is what it's going to look like. So you can define, with HTML tags, you basically define everything. You define your scene, you define the sky, you can put sources in if you want to use a sky texture. If you prefer to use a sky color, then you can put a color. Then you have this geometry primitives, as you have usually, boxes, spheres, cubes, whatever. Planes are also very prominent. And you can also define the lights. And that's where we come back to the beginning. Because with these components, you're gonna make or break your scene. If your lighting is good, you can really achieve a lot by just having 3 or 4 or 5 different objects in the scene. And the best part of A-Frame is that it comes with WebVR integration. So you don't have to do anything. You can just lean back, you import your Vive controls, or every major headset is supported. Also, mostly every major headset controller is supported. So this is what that example would look like for onesie.js. But that did not look very good. I mean, the background does, but the foreground. So it's still the big question in the room is, how do I get my 3D models? And that's where also we come in. So for example, this is going to be in your head of your HTML. You load all these external components. They're called A-Frame components. And I think the open source community is really doing an amazing job here, because you have all these really cool components like A-Frame orbit controls. You have people that are building environment presets for you. So you can just import them and say, I would like to use this preset. And then afterwards you can always use animation of each attribute to change your scene the way you want. And you can, if you don't like HTML, you can do that with JavaScript. So you can just edit your HTML attributes programmatically to make them animate. And this is how you're going to use the A-Frame components that are made by external parties. For example, you can load a 3D.io furniture of your choice. You can position it, because position attributes are just generally used for each object. And you can have your camera rotating around that object, and you had this really nice background that you love so much, and you just want to lay in that bed, and with the VR headset, yeah. So this, I think, is really cool, and you should definitely try it out, because there is so many amazing things that people are doing with this. I would like to share with you like a few tips and tricks. This would just be a talk on its own, but this is what I have been asked most of the times. Again, how do I get my 3D content? Should I go now and start to learn Blender? Because that's a pretty frustrating tool to learn. I know it. I've worked a lot with Blender, but it's pretty powerful. However, you don't have to do that, because some people, like my coworker Thomas, are writing inspector plugin for A-Frame. So A-Frame has a 3D inspector where you can manipulate your scene, drag around things, try out your values that you then can port into your HTML file. And you can use this inspector plugin to get models from, for example, Google Blocks. And just try it out, scale the models, have fun with it. Then lightning, not lightning, why do I always say lightning? Lighting is gonna make or break your scene. So I think it makes a really big difference. And if you're interested in this, I have high motivations to write blog posts about this topic. And then for the end is content optimization. We are people that work mostly with the web and with different devices. So if you start working with 3D for a project, think about what is your target group. If you want to use 3D on different devices at the same time, keep in mind that you might want to design it differently for whatever you want to do. If you want to do a fast-paced game, then you have to maybe not be so detailed. But if you want to do product, like you want to have a 3D scene of your product that you try to sell, you might want to be more detailed on that. So you should be thinking about loading your assets progressively. That means you could have your textures in different sizes or different formats depending on what your device is capable of doing. And you should design for level of detail. If there's an object in your scene that you're only going to see 2 pixels, don't make it have 1 million polygons, please. And these are all the lessons that we have for free from game development. Also, one other lesson that we are actually doing, or that I was working on, is we do use ray tracing for calculating light simulation for static scenery. So the parts of our scenes that are static, we use a ray tracing engine to calculate in the cloud what is our realistic light, and then we put it back into the rasterization with the real-time stuff. So this is also really cool workarounds. So 2 takeaways, and then I'm done. Models, materials, and lights do matter. And this one is mostly for myself. I love ray tracing, it's really cool, but are we ever gonna have it real time? NVIDIA is having really cool demos on this, but it's still a question that is unanswered. Thank you very much for listening. If there's any questions, please ask me anytime. And this is to get you started. So Scratch a Pixel is amazing resources for any computer graphics pioneers that would like to get started and really try the engine out themselves. A-Frame is the tool that I have been showing you if you just want to play around. And 3D.io is what we are working with to provide you with the models you need.